In a previous course, we defined the the work as the integral from position 1 to position 2 of a force in a dot product with the differential of position. We stated if we apply a force and this force exerts a displacement, then, well, we have performed a work. But work is also a change in the energy of the system, such that previously we have stated that the work equals the change in kinetic energy, the change in potential gravitational energy, the change in potential elastic energy. Let's now define the electric work. In the electric work, for instance, the force that we're applying is the electric force, for instance, K, Q1, Q2 over R squared in a differential of the R from position 1 to position 2. Well, this force is given, for instance, if we have a particle. So if we have one particle and we have an interaction between other particle, and I move this particle towards any given direction, for instance, well, if I move from position 1 to position 2, I will exert a work. And this work is given, for instance, well, the constants can go out from the integral, and we're going to have this integral, right? And this is going to be equal to minus k q1 q2 over r evaluated from r1 to r2. So we can have that the electric work is going to be equal to k q1 q2 over 1 over r1 minus 1 over r2. And this r, for instance, is the position. Let's state if this is my 0, it's going to be the position from where the charge starts. It is also very useful to state that this guy is going to be the integral of the charge, electric field, the R. So for instance, if we have a charge which is exerting, or let's not state a charge, let's state, for instance, a continuous distribution that is exerting a constant electric field, and we have, for instance, a charge here, and we're going to move towards this direction. Well, then what happens in this case? Q can go out of the integral, and if the electric field is constant during the whole position, we can take out the electric field, and this is going to be in R1, R2, the R, so that the electric work for constant electric fields is not happening that, for instance, in this charge. But if we have a distribution which exerts a constant electric field, it's going to be equal to QE times the change in position. So that's the work if I move this charge to this position. And since, well, you might remember from another course, if we have, for instance, the planetary system, right? This is the planetary system. And I have a mass here. And this mass, I move this mass from this position to this position. Well, the work was equal to mass times the gravitational field, right? Which is constant, the gravitational field, times the change in position, and this was the gravitational work. Well, the electric work seems pretty straightforward. We have a charge instead of mass, so we have a charge instead of mass, we have the electric field instead of the gravitational field, and we have the change in position instead of the change in and the change in position is the same, right? So if this is R1 and I move this to R2, then I exert a work. But we were also acquainted with the idea that if this position is the zero position, we can actually find this position, the position of the plate, as a zero position. This is a plate, for instance, or any given surface that is exerting an electric field. This is a planetary system that is exerting a gravitational field. I position my zero at the lowest point or at the source. And then I can actually state that at this position, I will have potential gravitational energy given as mgr1, or position 1. Well, I can actually state that I can have here, well, a potential electric energy given as QER1, right? If I define this as R1. So at the very end, the work and the electric work can also be given as a change in the potential electric energy. So this is the potential electric energy as well.